Well, thanks very much for the invitation to speak here. And I'll talk about a proposal that I made recently for the dual description of string theory on pure NS ADS3 backgrounds. And so the paper came out in October, but it's based on lots of previous work with Andrea Day and Matthias Gabedi, which I also mentioned during the talk. So let's start. So first of all, in string theory in ADS3 with pure NS flux is perhaps the most computationally accessible ADS background that we have in the framework of string theory, because we can just describe it using the RNS formalism, using standard worldsheet theory. And the relevant worldsheet theory is the sigma model on ADS3, which is nothing else than the SL2R WZW model. And but I would say that it's also among the least understood in terms of holography. We all know that there's the duality between ADS5 times S5 and NH4 super mills, ADS4 times S7, ADS7 times S4, all of those, the dual CFTs are very well, at least conjecturally understood. But in ADS3, where it's the background where we have essentially the most computational control from the string theory side, we don't know what the dual CFT is, which is a little bit weird. And I think the essential reason for this is that it has this unusual property that it has a continuous spectrum. So if you compute the string spectrum, and I'll explain this later again, then you find a discrete sector like we're used to in ADS5, let's say, but then there's also a continuous spectrum. So it's more like a hydrogen atom where you have some bound states and some scattering states. And so if you want to construct any sort of dual CFT, then we'll have to have some discrete sector and some continuous sector. And so it's some kind of non-compact space-time CFT where you just don't have a number of discrete states. But somehow in the literature, this was always somehow sold as a sickness of the background and why people didn't really look at pure NS ADS3 backgrounds. But I would really advocate that this is a feature of the background. We have to live with it, and it's not a bug. So this feature is very much like in Liouville theory, where you have a continuum spectrum, but still this theory is very nice and you can solve it and you can do all sorts of things. So indeed, it turns out that the dual CFT has many things in common with Liouville theory. All right. So there was some progress made on ADS3 backgrounds in the last 3 or 4 years. And there are essentially two arenas where this progress was made. One was a special kind of tensionless limit of ADS3 times S3 times T4, which is one of the backgrounds of type 2B superstring, let's say. And so there is so since it's NS flux background, there's some number of flux in the background that is labeled by an integer that I call K during the talk. So K also already appeared as the level of the WZW model. And if you put this integer to be its minimum value, so you'd have exactly 1 unit of flux, which is very far away from any kind of supergravity point or something, then the dual CF2 turned out to be just a symmetric orbifold of T4, which of course is Maldasena's original proposal. But this proposal here is slightly different. When Maldacena talked about the dual CFT, he was just saying that the symmetric product orbifold of T4 is on the same moduli space as the dual CFT to ADS3 times S3 times T4. And so this is an upgrade to the statement where we say that this background is exactly due to that, and you don't have to turn on any marginal deformations or anything like that. And a similar kind of progress was achieved recently for other very stringy backgrounds. So they have even K less than 1. And they're not of the form ADS3 times S3 times T4, but they have some other forms. And in this case, there was also a very convincing proposal by these people recently. And so we are somewhat emboldened by this and try to revisit now the generic NS background and try to say something about the dual CFT. Okay, so let's start. So the first half of the talk will be roughly a description of known things on the string side, and then we'll try to construct a CFT that reproduces all these things. So basically, that will be like a 2-point function and 3-point functions on this background. So to keep things simple, I will talk about bosonic strings, which is maybe a little bit weird, but trust me that there's a SUSY analog of this whole story, but it will just make all the slides more messy if I would tell you the SUSY story. And I will only talk exclusively about tree-level things. So I will compute, say, tree-level correlators and things like that. Tree-level, I mean genus 0 correlators, no higher genus corrections. And so the bosonic string is perfectly well defined in the setup. And so the word sheet theory is controlled by this SL2R algebra at level K. That's just because the word sheet sigma model is an SL2R WZW model. And the K that appears here we already encountered before. And it's basically telling you how big ADS is in units of string length. So if you make K very big, then ADS is big measured in units of string length. So the typical string inside ADS will be very small. So supergravity in particular is a good approximation to the theory. If you make K very small, like on the slide before, where the dual CFT is better understood, then the string is actually very large compared to ADS. So that's why it's also called the tensionless limit, because the string can become very large and there's no tension holding it back. Okay, so then I already mentioned that we have these two different kinds for the spectrum, and it's just essentially a consequence of the representation theory of this algebra SL2R level K. And so this algebra has two sectors, just as SL2R without level K, just the global SL2R algebra. So there are two different series of representations, unitary representations. One are sometimes called discrete representations, and they're essentially characterized by the fact that this spin, so there is an SL2R spin, which is the analog of the, say, SU2 spin. So this is the same algebra, just a different real form as SU2. And so for SU2, the spin would take half integers, or in this convention, negative half integer values. And so for SL2R, it would take real values, and normalizability of the representation imposes you also a bound on J. And then on top of this, there are so-called continuous representations, or sometimes principal series representations. And for those, the spin is actually complex. So it's in 1/2 plus IR. And on top of this, there's no bound on J now on this imaginary part, but there's a reflection symmetry that identifies J with 1 minus J. And so both of these types of representations lead to physical string states, and the ones coming from discrete representations are usually called short strings, and the one coming from continuous representations are called long strings. So this is just the representation theory of SL2R without putting in the affine structure. But the affine structure buys you one more thing, because you can also have winding strings in ADS3, and they're described by so-called spectrally flowed representations, which are particular kinds of representations of this affine algebra. And you don't need to know how they're defined. The only thing is that they're characterized by an additional integer w. So you can dress any representation up with some w, and you should interpret it as a winding. So let me show you a picture of that. I think that will make it more clear. So this is the space-time picture of these kind of representations. So the sort of vanilla easy string state looks something like this. So I drew here ADS3. The time goes up in this picture. So ADS3 would just be some infinite cylinder topologically. And so if I have some string propagating in ADS3, then the simplest string I can think of is some string that is just oscillating near the center of ADS3 somewhere. And so that's a typical short string state. So it's just oscillating. And it's also clear that this you should think of as being some kind of bound state inside ADS3. But it turns out that there's another possibility, namely long string. And for the long string looks more something like this. So at the infinite distant past, the string was huge and it was very close to the boundary. And then as time progresses, the string collapses inside. At some point, it's fully collapsed and then goes outwards again. And there's no oscillatory motion. It's just, it goes in once and goes out again. And this is this is a typical long string picture. So this comes from one of these principal series or continuous representations I told you. And the imaginary part of J here has the interpretation of being a radial momentum of this long string. And so you can already see that the long strings, they will lead probably to a continuous spectrum in your theory, because you can give them any amount of radial momentum. There's no quantization on this amount of radial momentum. Whereas these oscillating solutions, they will be quantized. And you can also see from this picture the winding number that I mentioned. So this short string here actually has no winding number, but this long string here has a winding number of 1, because the blue, like the blue string wordsheet winds once around the boundary of ADS3 asymptotically in, say, the infinite future. And now you can imagine that you're drawing the same picture, but the wordsheet is wrapping twice around the boundary, or 3 times, or whatever number of times you want. So you have all of these states, and they're all physical string states. And already to take away one thing is that the long strings here will have a much simpler holographic interpretation, because they are sort of scattering states. And the short strings, they will emerge as bound states once we discuss the dual CFT. And that also kind of makes sense, because the long strings, they reach all the way to the boundary, whereas the short strings never go near the boundary. So that's why the long strings have a sort of simpler description in the holographic description. Okay, then I also briefly want to mention vertex operators. So since I'm interested in mostly computing correlation functions, so these will be my main observables. And so there are vertex operators that are associated to these representations, and they're most naturally described in a Euclidean ADS setting. Since we're doing 2D CFTs, both on the wordsheet, and the dual CFT will be also 2D CFT, it's sort of natural to consider both as Euclidean CFTs, because we're most used to working with Euclidean 2D CFTs. And so it's also most natural to describe the whole thing in Euclidean ADS. So that's what I will do. And then the vertex operator for Euclidean ADS looks something like this. So I just want to highlight a little bit the various quantum numbers again. Sorry, the various quantum numbers that enter the vertex operator. So a vertex operator is characterized by the spin J that we encountered before, the winding number or spectral flow number. It has some definite space-time conformal weight. So since there is some space-time SL2R symmetry that corresponds to the space-time conformal symmetry of the dual CFT, there will be some conformal weight of every vertex operator. And additionally, maybe most interestingly, these vertex operators actually depend on 2 coordinates. So they depend, of course, on the wordsheet position, where I insert them on the wordsheet, but they also depend on the space-time position. Because here I drew again the schematically a picture of how such a correlation function would look like in Euclidean ADS3. So Euclidean ADS3 now, before we had an infinite cylinder, which is the Lorentzian version. The Euclidean version is just a ball. And then I have some, if I want to compute some stringy correlator, then I need to insert some vertex operators on the wordsheet, and the wordsheet is touching the boundary at various points. So this would be a 3-level 4-point function, a genus 0 4-point function, and there are 4 vertex operators inserted. And my drawing skills are not that great, perhaps, but 2 of these vertex operators have spectral flow or winding 1, because the wordsheet wraps once around the insertion point, and 2 of them have winding number 2, because the wordsheet wraps twice around the insertion point. And they have both a definite position z on the wordsheet, but also in space-time that I call x. And that's roughly speaking where the wordsheet touches the boundary sphere of Euclidean ADS3. So the boundary of Euclidean ADS3 is just a copy of the Riemann sphere. And so there is some definite position in space-time where this vertex operator lives. Okay. And now I just want to tell you very quickly what's known about these correlation functions. So essentially the 2-point functions are known, and they're known for a long time, and they're quite simple. So if you want to compute a 2-point function of 2 of these vertex operators on the wordsheet, then you get a bunch of delta functions, and you get 2 terms. And basically the fact that you get 2 terms is a consequence of this reflection symmetry. I told you at the beginning that, so this V, so there's an identification of the representation of spin J and 1 minus J. And since they are equivalent representations, you need to have both these delta functions here. And so the way you should read this is that so if these are vertex operators of long strings, then you should think of these long strings as being waves that are scattered at the potential wall, and there is an incoming piece and an outgoing piece. And they're related by a reflection coefficient here that I called R. And yeah, so everything is very similar to Liouville theory, if you're familiar with Liouville theory. And there's some explicit form of the reflection coefficient that you don't have to look at very precisely, but I just want to mention that it has various poles that are interesting, have interesting physical meaning. So there are essentially two series of poles. One is the so-called LSZ poles, and they arise due to the presence of short strings. So there are I mean, whenever you compute some correlation function in any theory, then there will be some poles, and whenever you have a pole, you know that there's some intermediate particle that goes on shell, roughly speaking. And so when you have a pole here, then you know that there is actually some bound state here. And so you can discover the short strings as poles in the correlation functions of long strings because they're bound states. So that's one way of basically discovering short strings. And on top of this, there are also other poles that don't involve these H's, but they're just poles in the spins. And so they're sometimes called bulk poles, and they arise because the target space of ADS3 is non-compact, and you have to do the path integral over all of ADS3, and because of the non-compactness, sometimes you get resonances, and they lead to poles in the correlation functions. So that's a very general story, and this is true for all correlation functions, not just the two-point function I mentioned here. So the three-point function, I just want to tell you essentially that it's also known since last year, and it's a kind of complicated formula, but it's very explicit. So we know everything about the three-point function that you want to possibly know. And again, this function has bulk poles, and it has LSZ poles corresponding to short string states going sort of on shell. And okay, so that's kind of great. So I just want to highlight this again, that so this is a background, an ADS background, where we do know all the two-point functions and three-point functions exactly in alpha prime, at least at tree level. So that's very much in contrast to, say, ADS5, where we don't know this. ADS5, the best we can do, which is already great, is to do some alpha prime expansion of the spectrum and things like that. But we are very, very far away from knowing something like a three-point function ADS5. It will be a hugely complicated object. So in ADS3, even though this formula looks complicated, we're in this great position that we know actually what the three-point function is. So now we can just turn around the logic that we're usually doing and saying, oh, we know what the space-time three-point function of our space-time CFT has to be. And so let's try to construct a CFT that has this given three-point function. And I'll do this sort of in two tries. So I make first a naive proposal, and then there's some problems, and we'll fix them. And so again, we are looking at the bosonic string theory on a background of the form ADS3 times X. And X is just any compact unitary internal CFT with the right central charge to make the background critical. And so we observed some time ago that the spectrum of long strings on this background actually matches a very simple CFT. And the CFT is just a symmetric product orbifold of some building block. And the building block is a free boson theory that I called RQ here. I put a Q because it's a background charge. It's a free boson with a background charge. And the background charge Q is just k minus 3 over root k minus 2. And then X was just the internals, the CFT describing the internal space. So there's some worldsheet theory for this background ADS3 times X, and we're just copying the CFT that describes the internal part here. And so this matches so this spectrum matches just the long string spectrum. And you should think of this RQ very roughly as a physical intuition. You started out with ADS3, which has 3 directions, but then you need to impose, say, a light cone gauge or any gauge fixing that you like, and you throw out 2 transverse, you throw out 2 directions through the gauge fixing. And so you just remain with 1 transverse direction in ADS3. And so the physical string spectrum will just behave effectively like ADS3 just consists of 1 direction. And you can think of RQ as being the radial direction of ADS3. Okay, good, but it cannot be quite right. So what the problem is that there are some problems. So for example, the CFT would have an exact U1 symmetry because there's a free boson with a background charge. So there's an exact anomalous, but still U1 symmetry. And this one is not there on the string side. So that can't be really right. But also we don't have reflection symmetry in this CFT, and we don't have any short string states at all. So that cannot really quite work. And basically what we're missing is that for when we computed the two-point function before, I told you that the long string states, they're kind of scattering states, and they're going into ADS3 and then they hit a wall and they get scattered back out. And there was some reflection coefficient that related the incoming and the outgoing wave. And we're basically missing the potential, the exponential potential that makes the string return. And so this is very similar to the relation of a linear dilaton theory and Liouville theory. So linear dilaton theory doesn't have some potential like that. And in Liouville theory, you add this potential on top to obtain some reflection symmetric theory. So let's do that. So we have to add a marginal operator to the theory that makes these long string modes reflect, and we get the reflection symmetry in the model. And it turns out that there's a very natural candidate that does it. And this candidate is essentially some exponential piece in our free boson direction. So that's called phi, this free boson direction RQ that we had before. We put some exponential vertex operator here. And then we have to dress it up with the twist 2 operator. So that's a new ingredient. In Liouville theory, you just have that your marginal operator would be something like e to the b phi or 2b phi, something like that. So you would add some marginal operator. And if you look at the Liouville action, that's exactly, you have this term in the action on top of that, of the like just free theory action. And this vertex operator is non-normalizable just because this vertex operator has some exponential shape. So near phi to minus infinity, it blows up exponentially. So very roughly speaking, it looks something like in this sketch. And now you have these ingoing waves that are marked with this red arrow, and then you get some scattering here in the left part of the picture, and then the wave returns and you get this blue reflected wave. So it's already clear that when you put in such a vertex operator and you deform the theory by such a non-normalizable marginal operator, then you will get a reflection symmetric theory, provided that this perturbation is well defined, which is not clear at the moment. So basically what we're now trying to attempt is to just define a dual CFT by perturbing in this phi field. And so if you want to compute any sort of correlation function in this dual CFT, then let's call the vertex operator, let's call the fields for now O alpha I. So the alpha I are the momenta of this free boson theory. And then you just define it by conformal perturbation theory. So you just insert order by order these marginal operators, you insert a bunch of them, you have to integrate over their locations, and then you have to sum over all the orders in this conformal perturbation theory. And since the deforming operator is non-normalizable, this is slightly subtle, and that's why I put the quotation marks around the equal sign. Because so the same happens in Liouville theory, and in Liouville theory it's well understood what you should do. That's basically the work of Dotsenko and Fatev. You have to sort of analytically continue the perturbation series. So what actually happens is that we're supposing that there is some consistent CFT that is defined by this perturbation, but what you compute by conformal perturbation theory are just residues of the correlators. So the correlators, there will be meromorphic functions in these momenta alpha I, and the residues are computed by the perturbation series. So that is exactly what you would do in Liouville theory, say. So where the actual correlator, say 3-point function, will be given by the DOZZ formula, and the DOZZ formula has a number of poles, and you can compute the residue of these poles using the Coulomb gas formalism, which is exactly doing this conformal perturbation theory. Okay, and so now basically that's what I just said. So we assume that there's some CFT that has these correlators, and the only thing that we can access computationally are the residues. And we're supposing that there is some consistent meromorphic function that has these residues. And it's not completely clear to us whether we can construct a CFT from first principles, or even whether it exists non-perturbatively. So we just like define it order by order in this conformal perturbation theory. But we conjecture that it exists, and we can make very, very convincing tests of it, as I'll explain to you in a second. And so at least perturbatively in the string coupling, this is the dual CFT, and that I'm pretty sure about. So there's a question of what happens non-perturbatively, and I won't make any statement about it in this talk. Okay, so before, I'll
Sorry,
wrap up very soon.
your time is about to finish.
Yeah, I wrap up very soon.
Okay.
I started, I think, 5 minutes late, so if that's okay. But I'll be done in 2 minutes.
Okay.
So just to explain you very quickly, there's a map of parameters. So the dual CFT depends on this coupling constant that you added to the marginal operator that we added. And then there's some n dependence where the n entered, that is the symmetric product orbifold with n copies. And actually, there's only one combination of them that appear in the large n limit, and it's this combination here that translates to the string coupling. So you might wonder why there are apparently too many constants in the parameters in the dual CFT. So both sides have the right number of parameters. And finally, I just want to mention that all the correlation functions that you can compute are, they do match. So you can check that if you compute a 3-point function using string theory, and I basically explained to you that, so the 3-point function in string theory, you compute by the 3-point function in void sheet theory. The only thing that you have to do is there is some normalization of the string pattern to go. So there's some constant in front, and you want it to match the 3-point function in the CFT. That's what holography tells you. And there's also some relative normalization of vertex operators. And you can check that all the poles that you have in the CFT correlators translates, and that we can compute in conformal perturbation theory, translates to bulk poles in the string correlator, and you can show that the full set of poles agrees. And you can also check that all the residues agree. So that I don't know how to do in closed form, but I checked up to 4th order in conformal perturbation theory. And given the complicatedness of all these functions here, it's quite amazing that this works out, I think. Finally, this is my last slide. We can find short string states in the CFT by looking at bound states. And so there are these LSZ types of poles in the correlator. And I mentioned to you that looking at these poles, you can discover the short strings. And basically now it's manifest, since the correlators of the string theory and the proposed dual CFT are already identical, you can deduce that the short string spectrum will be also identical. And so the full spectrum matches, both the discrete spectrum and the continuous spectrum. So now just to conclude, so that's just repeating my main proposal. The proposal was that the symmetric product orbifold of this free boson theory times x, where x was the internal CFT of the background alias 3 times x, deformed by this marginal operator phi, is the dual CFT, at least perturbatively in the string coupling to string theory on this pure SNS background. And we checked that all the 2-point functions and 3-point functions in conformal perturbation theory match, and the full spectrum gets also reproduced correctly. So at this point, it's almost a proof, because once you know that all the 2-point function and 3-point functions match, then you know that the CFT is uniquely specified. So with that, let me thank you, and I'm happy to answer any questions.